Supermaneuverability is the ability of aircraft to maintain pilot control and perform maneuvers in situations and ways exceeding those that are possible by pure aerodynamic mechanisms. This capability was first researched in the United States, and eventually resulted in the development of the McDonnell Douglas F-15 STOL MTD as a proof-of-concept aircraft, the result of research begun in 1975 at Langley Research Center, a full 8 years before the Russian Mig-29 claimed this as a new, revolutionary capability. The USAF abandoned the concept as counterproductive to BVR engagements as the Cobra maneuver leaves the aircraft in a state of near-zero energy, having bled off nearly all of its speed and performing the Pugachev's Cobra maneuver without gaining any compensating altitude in the process. Excepting one-on-one engagements, this leaves the aircraft very vulnerable to both missile and gun attack by a wingman or other hostile, even if the initial threat overshoots the supermaneuvered aircraft. In 1983 the Russian Mig-29 and in 1996 the Sukhoi Su-27 were deployed with this capability, which has since become a standard in their fourth and fifth generation aircraft. There has been some speculation, but the mechanism behind the supermaneuverability of the Russian aircraft is still unknown. However, post-STOL analyses are increasingly used in recent years to advance maneuverability via the use of thrust-vectoring engine nozzles. Russian emphasis on close-range slow-speed supermaneuverability runs counter to Western Euro maneuverability theory, which favors retaining kinetic energy to gain an increasingly better array of maneuvering options the longer an engagement endures. Aerodynamic maneuverability versus supermaneuverability. Traditional aircraft maneuvering is accomplished by altering the flow of air passing over the control surfaces of the aircraft to the ailerons, elevators, flaps, air brakes and rudder. Some of these control surfaces can be co-maneuvered such as in the ruddervators of a V-tail configuration but the basic properties are unaffected. When a control surface is moved to present an angle to the oncoming airflow, it alters the airflow around the surface, changing its pressure distribution, and thus applying a pitching, rolling, or yawing moment to the aircraft. The angle of control surface deflection and resulting directional force on the aircraft are controlled both by the pilot and the aircraft's inbuilt control systems to maintain the desired attitude, such as pitch, roll and heading, and also to perform aerobatic maneuvers that rapidly change the aircraft's attitude. For traditional maneuvering control to be maintained, the aircraft must maintain sufficient forward velocity and a sufficiently low angle of attack to provide airflow over the wings and also over its control surfaces. As airflow decreases, so does effectiveness of the control surfaces and thus the maneuverability. On the other hand, if the angle of attack exceeds its critical value, the airplane will stall. Pilots are trained to avoid stalls during aerobatic maneuvering and especially in combat, as a stall can permit an opponent to gain an advantageous position while the stalled aircraft's pilot attempts to recover. The speed at which an aircraft is capable of its maximum aerodynamic maneuverability is known as the corner airspeed. At any greater speed the control surfaces cannot operate at maximum effect due to either airframe stresses or induced instability from turbulent airflow over the control surface. At lower speeds the redirection of air over control surfaces, and thus the force applied to maneuver the aircraft, is reduced below the airframe's maximum capacity and thus the aircraft will not turn at its maximum rate. It is therefore desirable in aerobatic maneuvering to maintain corner velocity. In a supermaneuverable aircraft, the pilot can maintain a high degree of maneuverability below corner velocity, and at least limited altitude control without altitude loss below stall speed. Such an aircraft is capable of maneuvers that are impossible with a purely aerodynamic design. More recently, increased use of jet-powered, instrumented unmanned vehicles has increased the potential flyable angle of attack beyond 90 degrees and well into the post-stall safe flight domains, and has also replaced some of the traditional uses of wind tunnels. Evidence: there is no strict set of guidelines an aircraft must meet or features it must have in order to be classified as supermaneuverable. However, as supermaneuverability itself is defined, the ability of an aircraft to perform high-alpha maneuvers that are impossible for most aircraft is evidence of the aircraft's supermaneuverability. Such maneuvers include Pugachev's Cobra and the Herbst maneuver. Some aircraft are capable of performing Pugachev's Cobra without the aid of features that normally provide post-stall maneuvering such as thrust vectoring. Advanced fourth-generation fighters such as the Su-27, MiG-29 along with their variants have been documented as capable of performing this maneuver using normal, non-thrust vectoring engines. The ability of these aircraft to perform this maneuver is based on inherent instability like that of the F-16. The MiG-29 and Su-27 families of jets are designed for desirable post-stall behavior. Thus, when performing a maneuver like Pugachev's Cobra, the aircraft will stall as the nose pitches up and the airflow over the wing becomes separated, but naturally nose down even from a partially inverted position, allowing the pilot to recover complete control. The Cobra, as performed by non-thrust vectoring aircraft, still depends on the aircraft moving through air. However, it does not involve the aircraft's aerodynamic surfaces and normal laminar airflow, but rather the whole airframe as a solid shape traveling through air, and its center of gravity in relation to the thrust vector. Being performed under conditions far beyond normal aerodynamic control and well into a stall without thrust vectoring, this is a form of passive supermaneuverability, possible because of aircraft design rather than thrust vectoring, which provides a way to actively control the aircraft well outside of the normal flight envelope. The Herbst maneuver, however, is believed to be impossible without thrust vectoring as the J-turn requires a half roll in addition to pitching while the aircraft is stalled, which is impossible using conventional control surfaces. Pugachev's Cobra can be performed with less change in altitude if vectored thrust is used, as the aircraft can be made to pitch far more rapidly, both inducing the stall before the aircraft significantly gains altitude and recovering level attitude before altitude is lost. Characteristics: although as aforementioned no fixed set of features defines a supermaneuverable aircraft explicitly, virtually all aircraft considered supermaneuverable have a majority of common characteristics that aid in maneuverability and stall control. Post-stall characteristics equals. The key difference between a pure aerodynamic fighter and a supermaneuverable one is generally found in its post-stall characteristics. A stall, as aforementioned, happens when the flow of air over the top of the wing becomes separated due to a high angle of attack. The airfoil then loses its main source of lift and will not support the aircraft until normal airflow is restored over the top of the wing. The behavior of the aircraft in a stall is where the main difference can be observed between aerodynamic maneuverability and supermaneuverability. In a stall, traditional control surfaces, especially the ailerons, have little or no ability to change the aircraft's attitude. Most aircraft are designed to be stable and easily recoverable in such a situation. The aircraft will pitch nose down so that the angle of attack of the wings is reduced to match the aircraft's current direction, restoring normal airflow over the wings and control surfaces and enabling controlled flight. However, some aircraft will deep stall. The aircraft's design will inhibit or prevent a reduction in angle of attack to restore airflow. The F-16 has this flaw, due in part to its fly-by-wire controls, which under certain circumstances limit the ability of the pilot to point the nose of the aircraft downward to reduce angle of attack and recover. Neither an extreme pitch down nor a deep stall is desirable in a supermaneuverable aircraft. A supermaneuverable aircraft allows the pilot to maintain at least some control when the aircraft stalls, and to regain full control quickly. This is achieved largely by designing an aircraft that is highly maneuverable, but will not deep stall and will recover predictably and favorably. To that design, features are then added that allow the pilot to actively control the aircraft while in the stall, and retain or regain forward-level flight in an extremely shallow band of altitude that surpasses the capabilities of pure aerodynamic maneuvering. Thrust-to-weight ratio equals. A key feature of supermaneuvering fighters is a high thrust-to-weight ratio. That is, the comparison of the force produced by the engines to the aircraft's weight, which is the force of gravity on the aircraft. It is generally desirable in any aerobatic aircraft, as a high thrust-to-weight ratio allows the aircraft to recover velocity quickly after a high-G maneuver. In particular, a thrust-to-weight ratio greater than 1:1 is a critical threshold, as it allows the aircraft to maintain and even gain velocity in a nose-up attitude. Such a climb is based on sheer engine power, without any lift provided by the wings to counter gravity, and has become crucial to aerobatic maneuvers in the vertical. High thruster weight is essential to supermaneuvering fighters because it not only avoids many situations in which an aircraft can stall, but when the aircraft does stall, the high thruster-weight ratio allows the pilot to sharply increase forward speed even as the aircraft pitches nose down. This reduces the angle the nose must pitch down in order to meet the velocity vector, thus recovering more quickly from the stall. This allows stalls to be controlled. The pilot will intentionally stall the aircraft with a hard maneuver, then recover quickly with the high engine power. Beginning in the late 4th generation and through generation 4.5 of aircraft development, advances in engine efficiency and power enabled many fighters to approach and exceed thrust-to-weight ratios of 1:1. All current and planned 5th generation fighters will exceed this threshold. High aerodynamic maneuverability even though true supermaneuverability lies outside the realm of what is possible with pure aerodynamic control, the technologies that push aircraft into supermaneuvering capability are based on what is otherwise a conventional aerodynamically controlled design. Thus, a design that is highly maneuverable by traditional aerodynamics is a necessary base for a supermaneuverable fighter. Features such as large control surfaces which provide more force with less angular change from neutral which minimizes separation of airflow, lifting body design including the use of strakes, which allow the fuselage of the aircraft to create lift in addition to that of its wings, and low-drag design, particularly reducing drag at the leading edges of the aircraft such as its nose cone, wings and engine intake ducts, are all essential to creating a highly maneuverable aircraft. Some designs, like the F-16, are designed to be inherently unstable. That is, the aircraft, if completely uncontrolled, will not tend to return to level, stable flight after a disturbance as an inherently stable design will. Such designs require the use of a fly-by-wire system where a computer corrects for minor instabilities while also interpreting the pilot's input and manipulating the control surfaces to produce the desired behavior without inducing a loss of control. Thus corrected for, the instability of the design creates an aircraft that is highly maneuverable. Free from the self-limiting resistance that a stable design provides to desired maneuvers, an intentionally unstable design is capable of far higher rates of turn than would otherwise be possible. Canard Controls A canard is an elevator control surface placed forward of the wings. Sometimes, as with the B-1B, they are simply used to stabilize flexible portions of the fuselage or provide very minute attitude changes, but they are used often as a supplement to or full replacement of tail-mounted stabilators. The theory behind canards as the sole elevator surface is that no elevator configuration after the wings is truly satisfactory for maneuvering purposes. The airflow over the wings creates turbulence, however small, and thus affects elevators placed directly behind the wings. Placement below the wings exposes the elevators to even greater turbulence from underwing ordnance. The original solution to such problems, the T-tail, has been largely discredited as being prone to dangerous deep stalls. Other solutions like the V-tail place the combination rudder elevator surfaces out of the wing's airflow, but reduce the effectiveness of the control surface in the pure pitch and yaw axes. As a supplement to traditional elevators, canards vastly increase control surface area, and often increase the critical angle of attack of the wings as the canard directs air more directly toward the leading edge of the wing. They can also be designed to operate independently, thus also acting as ailerons. Canards are not a requirement, and can have disadvantages including reduced pilot visibility, increased mechanical complexity and fragility, and increased radar signature. The F-22, for example, does not incorporate canards, mostly for stealth reasons. Many technology demonstrators and maneuverability test beds such as the F-15 SMTD incorporated canards, even when the production aircraft they were based on did not. Production fighters like the Eurofighter Typhoon, Dassault Rafale and Saab Gripen all use a delta wing configuration with canard surfaces, while variants of the Su-27 including the Su-30, Su-30 MKI, Su-33 and Su-37 all use canards to supplement traditional tail-mounted elevators. Thrust vectoring. Though a high thrust-to-weight ratio and high aerodynamic maneuverability are found on both aerodynamic and supermaneuvering aircraft, the technology most directly linked to supermaneuverability is thrust vectoring, in which the geometry of the exhaust nozzle of a traditional jet engine can be modified to angle the engine's thrust in a direction other than directly to the rear. This applies force to the rear of the aircraft in the opposite direction, similar to a conventional control surface, but unlike a control surface, the force from the vectored thrust is dependent on current engine thrust, not airspeed. Thus thrust vectoring not only augments control surfaces at speed, but allows the aircraft to retain maximum maneuverability below corner speed and some attitude control below stall speed while in maneuvers. Technology demonstrators such as the X-31, F-16 Vista and F-15 SMTD were built to showcase the capabilities of an aircraft using this technology. It has since been incorporated into pre-production and production fighters such as the F-22 Raptor. Eastern Bloc design companies have also introduced this technology into variants of fourth-generation aircraft such as the MiG-29 and Su-27 to produce the MiG-29 OVT Tech Demonstrator and Su-30 MKI Air Superiority Fighter respectively, and planned fifth-generation Russian-designed aircraft such as the Pak-FA will use the technology as well. In addition, domestic Russian Su-30 fighters will be upgraded with thrust vectoring engines. Thrust vectoring is most useful while performing maneuvers such as the aerial J-turn, where the nose of the aircraft is pointed upwards. It is generally considered impossible, in fact, to perform a true J-turn maneuver without vectored thrust. Other maneuvers that are considered impossible to perform under control using only aerodynamic maneuvering include the bell and the controlled flat spin. Assessment: pilots can pitch the noses of supermaneuverable aircraft up to extreme angles of attack, allowing them to potentially gain an advantage, by being able to lock onto a target and fire at it, but at the expense of the altitude and/or speed of the aircraft. Quantifying such a potential advantage using metrics was not really possible in the early 1990s. Traditional metrics such as instantaneous or sustained turn rate plots did not highlight the differences which pilots described when flying such aircraft. Several research projects were conducted through the 1990s, and one in particular, entitled Performance Assessment of Fighter Aircraft Incorporating Advanced Technologies by Anthony Kutskera, not only reviewed the suitability of existing metrics to measure the effects of supermaneuverability, but went on to develop a new metric for quantifying advantages and disadvantages while in flight. The new metric allows a quantitative assessment of the aircraft to be made, in terms which designers, pilots and tacticians alike can easily understand, unlike many newer metrics which combined existing metrics to develop magic numbers which have little meaning. Supermaneuverable aircraft currently in use: Su-30 MKI, Dassault Rafale, Eurofighter Typhoon, Mike-1 MiG-35, Lockheed Martin F-22 Raptor, Sukhoi Su-35, Sukhoi T-50 Pak-FA. References